name is Richard, and I'm going to show you how to reconstitute desiccated primers. So, before I start, I want to say that this is a strategy that we use. Doesn't mean there's other ways of doing it. This just has worked for us. It's worked quite well. So what we do is, you order primers and they come in desiccated form. You can order them from Invitrogen, IDT, a couple other sources. You get so many nanomoles. For example, 47.28 or 39.4. There's usually a decimal point. You take the number of nanomoles you're given, it's always on the container, you take that number and you double that number and you add that much amount of 10 millimolar tris to your tube. Then that will bring you to a concentration of 500 micromolar. Okay? So here's your tube of desiccated primer. Let's just say you had 50.0 nanomoles of primer. If I had 50.0, I would add 100 microliters of 10 millimolar tris. Okay? Kind of watch what you add. Tris, you want to add tris, not TE. TE is tris, EDTA. EDTA, ethylene diamine tetracetic acid, is a chelating agent. It will cleat out calcium and magnesium. Well, calcium is necessary for nucleases, so it actually increases the stability of DNA. The downside, though, is magnesium is necessary for Taq polymerase, which is not to imply Taq polymerase is the only thing used in PCR. There's other polymerases other than Taq, but the most common is Taq. But the point is, if you cleat out the magnesium, you're going to inhibit or completely destroy your PCR reaction. So you always want to rehydrate, I would suggest, in 10 millimolar tris. Okay? So you add your tris to your desiccated primers, and I'll give you a 500 micromolar stock solution. Okay? This is like gold. Actually, it's more valuable than gold. Many times more valuable than gold as a weight. Anyhow, from the stock solution, you then make working solutions, which are more dilute. For example, this might be 10 micromolar or 30 micromolar, whatever you need. The concentration of these depends on the need. For example, if you were doing PCR, 10 micromolar might be an easy, convenient concentration. If you're doing sequencing, this 30 micromolar is pretty good because you don't have to put as much volume of primers in. So it really depends on what you're doing. Okay? So what's the math behind this? So, here's the math. And before I show this, the weakness of this method is it does not take into account the volume change of DNA. DNA does have a volume. We're going to assume the volume of DNA is so insignificant that it really doesn't make a bit of difference. But ultimately, the stock definition of molarity, this is not 100% on it. Okay? So here's how it works. So, let's just say you had 50 nanomoles. Okay? And you add 100 microliters, right? Well, 50 divided by 100, and I'm going to go through each step. I could do this in one step, but I just want to go through each step just to show the math behind it. So, I can rewrite this as 0.5 nanomoles over 1 microliter, right? Now, nano is basically just a stand-in for 10 to the negative 9th. Micro, or mu, is stand-in for 10 to the negative 6th. So I can rewrite this as 0.5 times 10 to the negative 9th moles over 1.0 times 10 to the negative 6th liters. Okay? Now, this question becomes, well, how do we make this a molarity? Well, what if we multiply the top and the bottom, the numerator and the denominator, by 1 to the 6th? Okay? If we do that, it's not going to change what the fraction says. It's going to change around the numbers somewhat, but what the fraction equals does not change. So, if I multiply this by 1 times 10 to the 6th, just do brackets here, and this by 1 times 10 to the 6th. Okay? scientific notation multiplication, right? 1 times 1 is 1. Negative 6 plus positive 6 is 0, right? 0.5 times 1 is 0.5. Negative 9 plus positive 6 is 10 to the negative third. Okay? 1 times 10 to the negative 0, I'm just going to start right down here, is what? Is 1. 1 liter. 0.5 times 10 to the negative third, well, negative to the negative third is milli, right? This is 0.5 millimole. Right? Now, moles divided by liters is what? Molarity. So this is really 0.5 millimolar. Okay? Now, millimolar, typically how I like to see things, and most times you're going to see it this way, is this number is going to be between 1 and 1,000. So 0.5 is just not really a good number. So I'm going to make this increase 3 orders of magnitude. So it's going to go 5, 50, 500, right? To balance out the scale, this, which is 10 to the negative third, will decrease 3 orders of magnitude. So 10 to the negative 4, 10 to the negative 5, 10 to the negative 6, right? And 10 to the negative 6 is what? Mu, or micro. So this is really 500 micromolar. And that's how we do our stock solutions. Now, again, I'll reiterate, this is not taking into account the volume change of DNA. DNA does have a volume. When we do this, we assume that the volume change of DNA is not present. So this is an approximation. But if you want to take into account the volume change of DNA, you can.